And today we have a last lecture by Gaetan Barrow on the quantum Airy structures. And today we will talk about the intersection theory behind it. So Gaetan, thanks.
Thank you. So the philosophy of today's talk, and I will give some support to the philosophy, and there's also some conjectures, things which are not known yet, is that, so we have obtained some basic quantum Airy structure, and for any of them, so we've seen example coming from W of GLR, but the philosophy should be valid in full generality for anything that come from VOA. Also, we don't have elements to support that yet. So there's a partition function, and there should be a class on the moduli space, or a family of classes. So omega Gn K1 Kn, where these were my integers labeling variables in the on with the partition function depending, such that the coefficients of the partition function should be expressed as an integral of the moduli space of curves of omega Gn K1 Kn. And so that could exist. You could ask for that in cohomology, or as a Cho class, you decide what is the most likely. So anything solved by topological recursion should be expressible as intersection numbers of some class. So I'm going to talk about that today. There's a second part of the philosophy which I'm not going to talk about, but which is basically known in all the cases where the first part is known, and conjectural in all the other cases, is that this Z should be a tau function of a suitable reduction of Kp. If I want to be more precise, when you were doing WGLR with the full cycle as a twist, you would expect RKP. If R equal to, you would expect KdV, and actually that's known in those cases. All right. So before really starting, let me give the concrete expression for the W generators in conformal weights 1 and 2. So in conformal weights 2, this is nothing but the Virasoro generator. And I will do that for WGLR. And here with the full twisting. So W1K is JRK, so you have to remember that JK are the Heisenberg modes, so it's H bar over dxk. If K is positive, it is 0 if K is 0. And it's minus K, X minus K if K is negative. And this, so normally you would have sum over K1 plus K2 is RK, a half JK1, JK2 normal ordered, so derivatives to the right. But because of the twisting, there's a certain factor here, which depends on the divisibility of K1 and K2. And there's a shift R squared minus 1 over 24, which only occurs for k equal 1. So that's in L1. And you're not doing LK because these satisfy Virasoro commutation relations.
Is that just some funny coincidence, the 24, or is there something modular behind this?
Well, how to say? It arises from some sums over roots of rth root of unity, this r squared minus 1 over 24. But of course, you know that 12 and 24 are always there when you look at Virasoro representations. So it's not more mysterious than it is in Virasoro. Let's put it that way. Okay. And what we did from that, so of course, there's also
nothing to do with an eta function.
If you look at the graded character of Virasoro, you would have for the standard module for Virasoro, you would get that. But this is a non-twisted case. So, but this is a normal ordering thing, so it's not surprising it occurs. And of course, if r is bigger than 2, then you have to go higher, and I'm not going to write those expressions because it's less explicit. So to get Airy structure, what we've seen is that we're shifting the variable xs for basic Airy structures. We take xs for some s and shift it by a constant, let's say -1. And the only interesting cases are when rs is like this, and we will get Airy structure when we have this congruence. If you go beyond, if you take s, which is bigger than that, it's not interesting because the partition function is equal to 1, so it doesn't contain any information. Okay, so let's do that for r equal 2. Then, so I can write, so the operators after shift, I write them h. So I have h1k, which is just j2k, and h2k, so the lk after shift. And this gives you 2k plus s minus a half sum of the j. So I have to distinguish between the odd and the even part because of these coefficients. So here I just write the odds. And then there's some even j's, which I'm not writing. And there's the shift. So delta k 0. Actually, I wrote 1 here. It's another convention. It should be 0. It's in L0 that you see this constant with an h bar. Okay, so when s is equal to 3, that's this maximal case. I should have that 2k plus 3 is positive. That's when I get my degree 1 term, which is a derivative. So that's what I want in the Airy structure. So I'm going to get LKs annihilate Z for k bigger than -1. So these are Virasoro constraints, including L-1 equation, L0 equation, etc. And if you write it in a more standard form with this derivative, from this you would get sum over m x to m plus 3, 2m plus 3, dx to m plus 1. For L0, you would get d over dx3 minus sum of x to m plus 1, 2m plus 1, dx to m plus 1, and there's an h bar, which I forgot. And here we're in the case where there's the constant shift, and etc. And if you want that to annihilate z, You may recognize from there what is called the string equation. And from this, the dilaton equation, which tell you some homogeneity. So x2m plus 1 is homogeneous of some degree 2m plus 1 for the dependence in Z. And then you have further equation. And so just writing that, if you know about Witten conjecture, Kontsevich theorem, you would realize that these are the Virasoro constraints for psi-class intersection. That is on the moduli space of stable curved. So a point there is a class of curves of genus G with endpoints, which must be stable. And you can consider the cotangent line at the ith point. This is a line. And when you vary the moduli, so when you vary this, it forms a line bundle, a holomorphic line bundle over MG n bar. So you can take its first Chern class, and that's called the psi class. And you want to consider integrals with some powers. They should match up to the dimension. If you want something non-zero, otherwise you find it to be 0. And this, once you put the correct prefactors, which are some combinatorial factor, the double factorials, this is equal to the FGNs for odd indices of this Airy structure. So for RS is 2, 3. So in fact, Witten's conjecture, there's two parts. There's the fact that this partition function of these numbers is a KdV tau function. That's strictly speaking what Kontsevich has proved. But then it was showed by Dagraf and the two Verlindes, if I remember, that this KdV tau function part implies the Virasoro constraints by some standard techniques. Around the same time.
Now, Gaetan,
Yeah.
so you didn't mention the quantum spectral curve at all.
No.
I know you want to do it from a different direction, but just a fundamental question that I've always puzzled about. There is a quantum spectral curve, isn't there, for all of these topological recursion problems?
Not known for all. Conjectured, but not known for all.
Well, when there is a quantum spectral curve, my question is, do the deformations which correspond to the parameters in the tau function, do they somehow preserve the can this quantum spectral curve be viewed as a difference or differential operator whose monodromy is preserved under the deformations?
Is that really true? Not for all deformations. For the primary deformations, I think yes, but not for all.
And that doesn't play, this isomonodromic aspect does not play any role in the topology?
I mean, I'm not sure it's true for all in full generality. You want us to be a bit more specific, and there needs to be assumption for these kind of things to be true.
Okay.
So this is the Airy structure way of formulating it. But the other way that some of you may already have seen is in terms of spectral curve topological recursion. And we've seen last time a general way to make the conversion. It means that you have to take, so the spectral curve is x equals z to the r, so here z to the square. And y encodes which dilaton shift did we do. And here we only did this one for x3. And that corresponds to do minus z over 2. The 2 is just because this is r, and the minus 1 is because we have just shifted by minus 1 here. So if you compute TR for this, you're going to obtain omega GNs. And if you follow the conversion, so the FGNs encode the coefficient of expansion of omega GN on a good basis of differentials. And here the good basis is, let me see, I think that here I must have a factor of 2. I'm not too sure that this one, or maybe it's inverse. And here this is dz over zi to mi plus 2 and 2mi plus 1 double factorial. And we're going to drag this double factorial, these combinatorial factors all the talk long. Okay, so now they must be there when you want to convert from spectral curve description to intersection theory description. And so this, in this form, this was something that NR had shown more than 15 years ago. Okay, so we did s equals 3. The only other case that we have for r equal 2 is s equal 1. That would correspond not to shift x3, but x1, and that corresponds to add to y a simple pole. And in that case, it's also known to be, it's actually the Brezin-Gross-Witten tau function of KdV. So it's a KdV tau function with a different initial condition than the previous one. And Nobbery had shown recently that there is a class, so he showed the existence of a class, which is in H2 G minus 2 plus N. So now it's not anymore, you would see here secretly the fundamental class of MGN bar that you intersect with psi classes. And now you have another class which has a certain fixed dimension. So that when you compute the omega GN for that curve, you obtain the intersection numbers of the theta class with the psi classes. These are not K's, these are M's. And this is on the same basis. And when I don't write omega 02, yes,
to say what the theta is?
So it's not extremely explicit, but Nobbery had shown it's a non-trivial fact that it exists. Well, actually, so there is a description in terms of the moduli space of two spin curves. And then you can look at the universal spin bundle on that. And you have to take the dual and push forward to the moduli space. So there's some algebraic geometry description, and then he proved that it has all the right properties to satisfy this.
I would like to just interject a little comment, which is, again, it's not really related to topological recursion, but it relates to these two examples. So maybe everyone knows this, but there's 2 or 3 interesting papers that have appeared at Archive in the last month or two, which prove that both of these integrals, both the Kontsevich-Witten and the Brezin-Gross one, are also, first of all, that every KdV tau function is a BKP tau function, everyone, and that it is not just any BKP tau function, but it is exactly a one of both of these are of hypergeometric type, which is exactly the kind of thing that occurs, for instance, in the generating functions for Hurwitz numbers as well. So this is a new result that is probably not widely known, but it's a very interesting result.
Okay. So we have these 2 basic cases.
Sorry, I also have a question. So this omega 02, I can think of it as a 2-point function of current operator.
Yes.
So these omega gn, maybe you said it in some previous lecture, but I don't remember. Can I understand them as some chiral correlators of something?
Yes, you can think of them as the, you see, okay, a little digression. The way we constructed our Airy structure is that we have a certain Fock module for the VOA given by W-GLR, like you have the Heisenberg VOA. And so there's a certain highest weight vector here. And so our Z is the highest weight vector. And now what can I do? If I just put it again here, I would just get 1. But what you can do, you can look at current correlation functions. And these essentially are going to be related to the omega GNs.
I see. So they're
Is it the full currents or just the positive part?
I think it is, yeah, it's probably only the containing negative powers of Z.
I see. And there are no vertex operators involved.
So that's for the basic case.
Okay.
Now we've seen that all the other Airy structure can be obtained by acting by some operators. And for very specific choice of these symmetry operators, if you want, you could try to insert some vertex operator here. There's going to be your new vector. And in that case, you can indeed see that this is your background vector. And you still look at current correlation functions. And this is more developed, this point of view is developed in the work of NR and Belliard. So they have some work on the TODA, WGLR, CFTs. They do that for any central charge, where here we only did the central charge equal to R. And somehow they postulate some axiom which essentially amounts to say that you have some vector generated by some vertex operator on this thing. And then they show that this current correlation function can be obtained by the topological recursion.
Okay. Thank you.
So out of those basic cases, we want to see what happens for a higher R. So if you do S equal R plus 1 and R, then indeed, when there's also, we can also rely this philosophy. It's done by the Witten R-spin class. So what you do is that you fix A1, AN, which belong to 1R. And you're going to look at the moduli space MGN R spin A1, AN. So it's genus G curves with n points and a certain line bundle together with some isomorphism to KC, so the canonical twisted with the AIs -1 at the PIs. So you want zeros of order AI -1. And the isomorphism is here. So on this, you can look at the universal line bundle over the universal curve. And from this, you can construct a class. So normally you would like to construct a class, and that's what Witten had proposed. But if you try to do it in practice, it only works in genus 0. So what you do that you're going to take the top Chern class of the derived push forward. Here I have the projection to MGN. And here everything can be compactified. So the first derived push forward of L, you take the dual and then you normalize properly. This is WGN R spin A1AN. And this is okay because this thing is actually a bundle in genus 0. And in higher genus, it's much harder to construct, but it has been done that such a class exists in Cho, so the Cho class. And so it's sort of replaced the fundamental class for MGN bar R spin.
Gitta?
Yes.
Is the Z also a tau function? And if so, is it of hypergeometric type?
Hypergeometric type, I don't know, but here it's also a tau function. So this was constructed in several steps by Polishuk and Weintraub, and it was revisited by Kyodo later in terms of K theory. So it's hard work. It's a bit hard to get one's hand on this class, but it exists. And it has nice properties. In particular, it's a cohomological field theory. Also, I'm not going to explain what that means. So then the statement is that if you take this curve, which corresponds to our basic Airy structure for S equal R plus 1, the omega GNs is a sum over all possible indices, M1, Mn non-negative, of intersection of this Witten R-spin class against psi classes. And now the basis of differential on which you can read those coefficients is dzi. There's rmi plus ai, the r-fold factorial, over zi rmi plus ai plus 1, where this symbol it generalized to r bigger than 2. What you know is the double factorial. So it's rm plus a, rm minus 1 plus a, etc. up to you arrive to a.
Is it still a multi-current correlator?
Yeah, what I explained here, I mean, you have a Fock module for WGLR. So yes, it is. And so the partition function, which I denote ZRR plus 1 here, is also, it's an RKdV tau function. And that's a deep theorem of Faber, Shadwin, and Zvonkin that uses given tau formalism. Actually, it's in one of these papers, but they also prove that given tau group preserves cohomological field theory to all genera. And then I think that it was proved, and there's different ways to say that's also the descendant potential of the AR minus 1 singularity. And so using some work of Milanov, this also proves the W constraint. And Milanov, I think it was around maybe 13, I'm not too sure, actually proved that these higher topological recursions, so here you see that you have a higher order branch point, those compute these intersection numbers, or if you want, the AR minus 1 descendant potential. So these are all non-trivial theorems. In particular, I would say that also this one here now has many different proofs, and including some geometric proofs, totally geometric proofs. This one, I must say that it's purely algebraic proof. At some step, there's some algebra which involves the W-GLR, and it's not clear to me how to reformulate, how to give a purely geometric proof of that, especially because here this is possible to attack this in terms of integral of some differential forms. That's what essentially one step of Kontsevich proof. Whereas here it's really not even a cohomology class, it exists in Chow. So it's hard to get measure theoretic and directly differential geometric understanding of it.
You said the RKdV?
Yes.
So that means it only depends on the KP flow parameters that are congruent to 1 mod R.
Yes, and you can see it here.
No. That means that it's congruent to everything that's not congruent
not
to
modular
0.
R.
Not,
It doesn't depend
So-
on the times
you
XR,
leave out the
XR,
mod R.
X3R,
Yeah. You leave out
because
the
you
mod.
have this constraint.
Okay.
So indeed here, I don't have to allow, it's not necessarily, I mean, the terms where sum of the A is equal to R is not contributing. I could put R minus 1 if I wanted.
But Gaetan, we somehow don't have a, so to speak, a finer structure because we have a sum over A, right? So we don't somehow.
No, you distinguish them because that's, you see the power of Z that you have. MI is just telling you what's the multiple of R, and then there's this residue, the Euclidean division. So you see all of them. Okay. So if you move to S different from, I mean, smaller than R, then what? So the curve would be X is Z to the R, Y equal Z to the S minus R over R. So Y as a pole. So there should exist a class. So that you have a similar formula, but it's conjectural. And if it existed, since you know what are, you know, the W constraints for this Airy structure, you can write down, for example, you know, the Virasoro operator, which are quite explicit. In particular here, you get a Dilaton equation And this dilaton equation is telling you that if you look at the pool, so with probabilities, some probabilities we can deduce. So one of them is homogeneity. So if it exists, since we think this is in Chow, maybe let's just assume that it exists in Chow. Then the codimension of this should be R minus 2. Oh, sorry. Should be 2 sum of the AIs minus S2G minus 2 plus N over R plus 3G minus 3 plus N. It's something you can deduce from the topological recursion. You would have a dilaton equation that would tell you that if you look at, so dilaton is what happened when you forget a point. So you can try to pull back the class from MGN to MGN plus 1. And then you have a modified axiom, which is like in Norbury's, the first time it occurred was in Norbury's theta class. But this dilaton equation we have, so as the L0 constraint, tell us it should also be true here, that when you pull back, if you multiply by psi n plus 1, you should obtain the RS class for n plus 1 and with insertion S, which plays the role of the unit. And then you would have some other evaluations, like omega 1, 1. So genus 1, 1 puncture should be R squared minus 1 over 24 psi 1 when A is equal to S and 0 otherwise. And likewise, omega 03 RS is known. So we have some ideas to construct it, but there's some technical difficulties. So generalizing what Norbury did, but it doesn't seem to exactly work. So it's a bit strange for the moment. We don't really know what the nature of this class is in general, but a strong evidence it should exist. And likewise, there should be a tau function. And here, so De Jong told me that for S equal 1, he constructed it. But actually, I think that Marco Bertola also has a construction of that actually occurred before that. It's the kind of R version of Brezan-Gross-Witten. But for the other values of S, doesn't seem to be known. Okay, so that's as far as we can go for what is known. But now I want to show you what you can do with that. Because we've only used very basic spectral curves. And we've seen that any other spectral curve can be obtained by acting with symmetries. Oh, actually, there's a question that I only see now by Ezra. There is no known way to formulate this theorem as statements about volumes of symplectic manifolds. Yes, there is. That's what I meant when I see here there's a geometric proof. So there is, so first, what Kontsevich did was expressing that as volume of symplectic manifolds apart from some zero measure set, which is the combinatorial moduli spaces. And then there's a way to prove the Virasoro constraints for these volumes in a way totally parallel to Mirzakhani's proofs in the hyperbolic case.
Gaetan, but I think Ezra asked about R-spin structures.
Oh, the R spin, I don't know any way to do that. I would be very happy if you had any insight about that. Good. So symmetries. So I recall that, so we just look at spectral curves which are smooth and one ramification point. The many ramification point case can be deduced by just summing several copies of W constraints. So we always have a local coordinator that x is e to the r. And y, we encoded that its expansion into some coefficients f0 k. And finally, we had omega 02, which could be arbitrary. And that was encoded in some coefficients f02. And from this, we had seen that we take the basic partition function and we act on it with T, which was a translation operator, and B, which was a change of polarization. And then the theorem that we've seen last time is that the WGs, GNs, are decomposed with the coefficients of the partition function of the Airy structure when we use a certain basis D minus chi xi constructed from omega 02. Okay. So what we have seen before is that these FGNs, in the basic cases, when I don't have these shifts, up to some combinatorial factors here, so that was essentially our D psi minus 2 mi plus 1. And then there's this extra factor over here. And there it was this R factorial, R fold factorial. So this basis D psi k is not the one adapted to intersection theory interpretations. So let's do a change of basis. I can look at Laurent series in Z. And I have some operator which I denote L, which goes in so formal series in the variable U. And so it comes in two flavor. Either I take the d psi k, which is zk minus 1 dz. And this one with a k. This one, I would like to send it to, that's not the k here, so I have to do that. U to the k over r. And d psi minus k, which was the one that we're really interested in to decompose the omega GNs. We would like to send it to k r fold factorial u to the k over r, because we know that's what's really related to, actually it's rather here, when it appears here, we want to replace that just with u to the k over r. So here it's formal power series in UR. So I really have L plus and L minus. And we don't really like fractional powers, so let's change that a little. Let's replace this by a R-dimensional vector space with formal series with integer powers of u. And here, I'm going to send that to, so the same factor, but this u to the kr, I'm going to send it to EA u to the m when I write k to be mr plus a in 1r, m positive. And I would do something similar here. EA u to the m. So that's the basis adapted to intersection theory. And that's the one adapted to spectral curves. So in the basic case that we've seen before, I can reinterpret what happens if I do L minus tensor n on omega gn. So let's look at these formulas. We just take that, this d psi minus rmi plus ai times the rmi plus ai the r fold factorial. And we replace that by EA u to the m. So EAI u to the mi. But then I can do the sum over the m's. And therefore, what you would find is that there is this RS class. So either when it exists, it is within R spin class or Norbury class, or when it doesn't exist yet, assume it exists. Then you can rewrite this formula like this. Sum over now finite sum. And you get a geometric series with psi classes. So this has the flavor of an ELSV formula. It's a class, and you intersect with 1 over 1 minus a variable times the psi classes, interpreted as you just expand the geometric series and you get powers of psi. And this terminates because the dimension of your moduli space is bounded. So the principle what I want to write now is that the action of the symmetries here, so this B hat and T hat operator, which we define here, we want to transport it here, and that will become symmetries acting on, acting on intersection on cohomology classes or Chow classes. And the second remark is that I define just on the basis what is this isomorphism L, but it has an interpretation for the geometry of the spectral curve. So if I do L minus, for instance, acting on a one form, I can rewrite it as a Laplace transform. Like this, where this is some coefficient expressed in terms of gamma functions. And gamma j is going in the jth sheet from 0 to infinity. That means in direction 2I pi j over r. There might be a minus sign here. So this is a Laplace transform. And there's a similar formula for L plus. Now this is gamma j exponential of minus z to the r over ur f. So we're going to define translation t and the change of and the effect of b on classes. So for translation t, you just write L of omega 0, 1. Omega 0, 1 is y dx, so it's something which is holomorphic, so only containing positive powers of z. So I can use L plus. And you get some series. In U, and I want to write it like this. So T Rd plus A, Rm plus A, EAUM. And then we act on the class. So omega GNRS by something that is familiar from the given tile group. You're going to take the class at n plus L, and you insert EA1, EAL. So I replaced, before there was some indices B's. And instead of writing B, I just write that this is, I just write that it's applied to the vector, it gives the B's. So I see it as a tensor. And 1 over L factorial, so I have these insertions. Here I have my B's. And I have a class on MG n plus L. But I want to get down to MGN. So what you do that you do a push forward of this. You can do that with Poincare duality in the cohomology ring, or also in the Chow ring, that works. And here, what should I put? So I want to do that. I also want to put some psi classes to the power m. And I do that with coefficients which are given by the t's. And the properties of the RS class, so in particular, you can do that for the Witten class or for the fundamental class, imply this is well defined. By dimension, for dimensional reasons, at some point, the dimension of that is going to exceed the dimension of the moduli space of curves. So that's for the translation. Then for the B, again, you write L plus on omega 02 minus omega 02 standard, which is a holomorphic thing. So you get some coefficients B, A1, A2, M1, M2. And you define the action on any class to be given by a sum over stable graphs. So like in given Tal formalism. That means so stable graph is a boundary stratum of the moduli of the Riemann-Ford moduli space. So you have the usual moduli space at the vertices. And you can think of that as a degeneration. And so this is a product of some moduli spaces here over vertices. And so you have a map, which is the inclusion of boundary stratum, pi gamma. And here you just take the product at the vertices of your class at the vertex with the good indices that were already here. And on the edges, you're going to see these, which I can call B U1, U2. You see B psi 1, EA1. So maybe I write psi 1, A1, psi 2, A2, which means you take the psi class, but you make the corresponding index here of this moduli space, which contains some A to be exactly that A. Good. And so the final theorem, and in this form, in this general form that's in the paper with Rainier and Yannick, is that for any smooth admissible spectral curve, meaning for which we have an Airy structure, L, if you write omega attached to the spectral curve, which is B hat T hat of the basic RS class, then you have that the Laplace transform of omega Gn is given by an ELSV-like formula for exactly that class. Good. So I think my time is almost over, or already over.
Can I just stress that this theorem is like dependent on the fact that omega RS has to exist?
Yes, if RS exists, which is already known for S equal R plus 1 and for R equal 2, S equal 1 or 2 or 3. So we just demand that this class, somebody constructs it, and then you would have that in general for any smooth spectral curve. You have an intersection theoretic representation of the omega GNs. So to really conclude, because the time is over, for R equal 2, S equal 3, so regular spectral curves, so Y regular, this is a theorem of NR. We're attached to any spectral curve with simple ramification points a certain class. And it already gives tons of applications. If you do the spectral curve of describing Hurwitz theory, then your class here, you compute it with as action on the fundamental class, and you find the dual Hodge class. And so you get back the LSV formula once you know that topological recursion is satisfied by the simple Hurwitz numbers. But you can take any of the others, like this one. Then you obtain what is called the Kyoto class. And you describe the R-spin Hurwitz numbers. Essentially, anytime you have a spectral curve, so here I did the case with simple ramification, just compute this Laplace transform is going to give you a class so that you have an LSV-like formula. This is also part of the ingredient by which it was proved that the mirror, if you take the mirror curve of a toric Calabi-Yau, then what you obtain is the Gromov-Witten class of X. Now, two subtotals I'm not discussing.
For the R spin, is it y to the R downstairs?
You're right, it's probably Y.
Thanks.
So there's many others here. The second point, which was already noticed by NR for R equal 2, and which we generalized with Rainier and Yannick. Here it's only about local curves, what we did. But imagine that you have a global curve, in the sense that X and Y, so what you actually need is that dx is meromorphic on a compact Riemann surface. And omega 02 is also globally defined with only pole on the diagonal. Then there's a nice property, which is that this BU1, U2, which was a Laplace transform of omega 02 minus the singularity, actually factorizes. And the factorization is pretty nice. So strictly speaking, this is projection on, so projecting out the ER, so these kind of times, depending on the index, which is divisible by R. So the one that don't appear in the RKDV tau function. These have a bit of a special role, and then the structure of the formula, also this kind of factorization, but it's a bit different. So when you project out this, there's a nice factorization like that, where essentially R of U is something like that. I'm not very precise here. But this is given tal R matrix. So you don't have a bivariate generating series, you just have a one variate generating series to construct. And then this operator B hat, when it comes from this R matrices here, so from a global geometry, is an element of the given tal group.
But is it for simple ramification or for any?
Any. It was known to Bertrand for simple ramification, and it's not very hard to prove it for any R. The only difference is the way you take the Laplace transform, which I said here. You have to use this kind of special symbols. And you see this constant here involve the gamma function. So it looks like something related to the gamma class in Gromov-Witten theory in this very simple case, but I couldn't make that more precise at the moment. And so this retrieves, for R equal to, it retrieves the result of DOS, so Dunin-Barkowski, Orentin, Chadwin, and Spitz, who proved that simple coFTs, semi-simple coFTs, are computed by correlation functions. That means intersection series of these coFTs with psi classes computed by TR. That appears as a special case of that. Thank you for your patience. I'm finished.
Thank you very much. Some questions, please. I see that there are many questions of Ezra. Ezra, are you happy or you want to ask something?
You can ask something even if you're happy.
Yes.
Okay, I'm not Ezra, but I get on some, may I ask some simple questions. So because if we come back to this ABCD
Yes.
part of the business, if we have this R spin, of course, it will not be ABCD, it will be something like ABCD, EFG, and
Yes,
so on.
exactly.
But for the simple spectral curve, it must be a known answer. So basically, we must know some explicit formulas for these coefficients. That's
Yes.
I was asking several times, but I never see anything written.
So for the ABCD, the case of simple ramification, this is in
No. For simple, that's we know. No, I mean.
And for the R case, this is, so I briefly flashed the formulas, I think, in the second talk. For the W generators in the basic case, so that would be those basic curves, RS curve here. It is in our paper with Vincent, Nitin, Thomas, and Dimitri.
Mm-hmm.
And then if you want to get for general spectral curve with other R ramification point, you just apply the change of polarization and the translation. So it's also not too complicated to write
That's
down.
clear. Yeah, no, I just asked for the simplest ever.
So I must say that R equals 3, completely explicit. If you were asking me on a rainy afternoon, I could compute for you completely explicitly R equals 4 as well. But there were these coefficients psi, j, some roots of unities here, sums of roots of unity, which were involving denominators. And then, okay, sum of roots of unities. And these ones, I have a closed formula for j. So for any I and j equals 0, so that's no quantum correction, so not the D case. The classical part is explicit.
Mm-hmm.
The j equal 1, so the first quantum correction, so like the D case, is explicit. I can get some expression, I mean, little by little, but I don't get a closed formula for any j.
That's strange, right?
Because it's going to be piecewise linear polynomial in the A's. And it starts to be a bit tricky to write down. I don't know a closed formula.
Okay, it's just so we will not discuss it right now, but it's just to mention there is possibly some interesting part hidden here.
That would be nice to have a closed expression indeed.
Could I just slip in a question which is sort of related? Is it the case that when you have a quantum spectral curve, in all these RS examples, that it is either a local differential equation or a finite difference equation or a Q difference equation?
So all those cases, I mean, the quantum curve should be a quantization of the spectral curve. So you know what is the quantum curve for, so let's write that. the case that you probably know very well, the Airy case. So in that case, it means that x is y squared, and quantization tells you, well, just replace this by that. And indeed, the quantum curve for that case is this. It quantizes this Airy equation. So that's well known since a long time, since essentially Kac-Schwarz. For the Bessel case, which is this related to this Norbury class, it's also known. And it's again the same. There's no specific quantum correction. If you do this R spin case, it's also known. It's S equal R plus 1. And essentially, there's no surprise. The Kac-Schwarz operator for this RKdV tau function. So it is something that I've started to discuss with you, and also Vincent Bouchard has started to think about it. It's the computation. I don't think anybody has done the computation. It wouldn't be very surprising. The results, I think, would be the following one. The equation is this. If I forget some constant in front of y. So the equation is actually y. Let's see how I can write it. So x to the s minus r, y to the r should be equal to 1. So y to the r is x to the r minus s. So I think the equation would be that. So s is negative, is smaller than r plus 1. Therefore, this is going to be a singularity at x equals 0. So this is my guess.
Yeah, well, it's also true for all of the weighted Hurwitz numbers with any weight generating function that is rational.
Yeah, so if you can handle the case where you have these higher order simple ramification, higher order ramification for x and also poles in y, if you can handle it with your techniques, then you get the result.
Well, there was one case which is a little bit, I don't think anyone is very interested in it, but it's what I call the quantum Hurwitz. So the weight generating function is not just a simple exponential or rational function, it's a quantum dilogarithm. And if you write down the quantum spectral curve for that case, it looks like it wants to be a Q difference equation, but we were not able to put it in such a form.
Yeah, so the point about these basic quantum curves is that I would expect there's no quantum corrections, and it should be just very simple. There's there's obvious quantization of the curve. And then you can maybe start from there to see if you can deform that to more interesting curves. So here, essentially, there's no normal ordering issue, which is a thing that you would have when you start to have quantum difference equation. You would have some powers of Q that comes up that disappear in the classical limit, but that they are there in the quantum differential equation. And this is known in some cases, but not in all.
Hi, Gaetan.
Hi, Danny.
So can I ask a question about the spectral curves? So yeah. Together with Ale and Paul Norbury, we were considering some classes, some extension. Right? So if you have a parameter t, and in the Kyoto class, you put the first parameter equal to 2t, and the second one to minus t. So those are the parameter choice. And I was wondering whether that could fit in some way in the picture.
It's an idea that many people had, and Paul had, that many people had somehow discussed with others. So I think Rand Tessler, Paul Norbury, Vincent, I think Ali at some point was also thinking about that. How to realize this RS class, a bit using the same idea that Paul had. So a very natural thing to do is to look at the top Chern class of Kyoto, which I think is for R and R minus S. or S minus R, I don't remember. So you have this Kyoto bundle, and you look at the top Chern class here, and then you push everything forward to the moduli space. And it seems to have, it has the right homogeneity. It seems to have the right dilaton, I think. For the other axiom, this very special axiom here, I mean, it seems to have the right behavior like this. And there's this very special axiom here. I'm not sure if it is proved or not. But this is not all. It doesn't uniquely specify the class. And the problem is that you would expect, okay, I know Kyoto, I can also add a weighting parameter related to the cohomological degree that deform the spectral curve. You go from this R spin S orbifold or R minus S orbifold Hurwitz number curve to some parameter T, where in the limit T goes to 0, you would get the top Chern class. That's easy to prove. But on the TR side, you would get to a situation where all ramification points collide to become an R order ramification point. And this limit is singular in the sense it doesn't commute a priori with the topological recursion.
Mm-hmm.
And therefore, that's where we are stuck with Vincent. Nitin did a lot of computations with that. Is that it seems in some case, actually, when S is equal to R minus 1, it seemed to be true that TR commutes with the limit. But it is certainly wrong if S is bigger than R minus 1. There are extra explicit terms that don't vanish. So you know that the limit when T goes to 0 properly renormalized of the omega G and T is given by intersection of this top Kyoto. But what you don't know is that this is omega G and TR for the T equals 0 spectral curve. And that's even wrong in that case here.
I see. So
that's why I'm saying it's a bit mysterious. We believe that for S equal R minus 1, this is the correct class. But then there would be a slightly different class differing by some terms. I don't know which one, which should give the answer for the other S cases. And that's a bit mysterious.
Thanks.
Okay, if there are no more questions, I will stop recording. Or someone wants to ask Gaetan something. Okay, I think we can stop now.